Hello friends, I welcome you in lecture number 6 on binomial distribution. In this lecture we will discuss one example on binomial distribution, and this problem is asked in GTU summer 2021 examination. So first we try to understand what is given and what we have to do in this problem. So the probability that an item produced by a machine will be defective is 1 by 10. If 12 such items are produced, find the probability that exactly one item will be defective, find the probability of at least 2 items to be defective, and find the probability that none of the item is defective. So here we are given that the probability that item will be defective is 1 by 10, and 12 items are produced, and for each item we have two possibilities: either the item is defective or item is non-defective, and we are asked to calculate these probabilities. So we can define first that suppose random variable capital X is equal to number of defective items. So here we have a sample of n equal to 12 items. Okay, here the number of items produced are 12, so we consider n equal to 12, and we take x equal to number of defective items. Now for each item there are two possibilities: either item is defective or item is non-defective. So if we define success as, suppose success denotes the event that item is defective. Okay, we consider success as item is defective or defective item. So here we have 12 items, that is n equal to 12. So we have a finite number of items or finite number of trials, and for each item there are only two possibilities: either item is defective or item is non-defective. Also it is given that probability of defective item is 1 by 10. So for each trial this probability of success is constant, it is 1 by 10. So probability of defective item which we have considered as success is given to be p equal to 1 by 10, and it remains constant for each trial. Also trials are independent, that means it does not depend on another item. If one item is defective, then the other items may be defective or non-defective. So the item is defective, that is trials are independent. For each item we can check for each item. So suppose we consider first item, then for second item whether it is defective or non-defective, that does not depend on the first item. So in that sense, that the item is defective does not depend on the defectiveness or non-defectiveness of other items. So we can say that trials are independent. So all the conditions of binomial random experiment are satisfied. The conditions are: first condition is number of trials are finite. So here n equal to 12, so we have 12 items which is finite, and items are independent. Also for each item there are only two possibilities: whether item is defective or item is non-defective. And fourth condition is probability of item being defective remains constant for each item. Okay, so here if we define capital X equal to number of defective items, then the possible values of X, possible values of random variable X are, so we have 12 items and X is number of defective items. So there is a possibility that out of those 12 items no item is defective, that means x can take value 0. There is a possibility that only one item is defective. There is a possibility that two items are defective, and so on. There is a possibility that all the items, that is 12 items, are defective. So possible values of this random variable are x is from 0, 1, 2 up to 12. So here x is a binomial random variable. So if we have binomial random variable, the probability mass function of x is probability that capital X equal to x equal to, we have ready-made formula for the probability mass function of binomial random variable, p raised to x 1 minus p raised to n minus x. X is from 0, 1, 2 up to n. So we put values of small p and n. N is 12 here, p is 0.1, so 0.1 to the power x. 1 minus p, that is 1 minus 0.1, that is 0.9 raised to n minus x, that is 12 minus x, and x is from 0, 1, 2 up to 12. So this gives us the probability of x defective items. The random variable capital X is number of defective items. So out of 12 defective items, this gives us the probability of x defective items. So if I want to find out probability of 3 defective items, I will calculate value of this probability mass function at x equal to 3 and so on. So this gives me the probability of x defective items among given 12 defective items. Now we check which probabilities we have to find out. So in the first part, we are asked to find out probability that exactly one item will be defective. So we try to find out all these things one by one. So probability that exactly one item will be defective or probability of one defective item. So we can use this formula. Here we can put x equal small x equal to 1. So this is equal to probability that capital X equal to small x, which is 1, and now we can put x equal to 1 in this right hand side. So we have 12c1 0.1 raised to 1 and 0.9 raised to 11. 12c1 0.1 to the power x, which is 1, and 0.9 to the power 12 minus 1, which is 11. Now 12c1 is 12, this is 0.1 times 0.99, okay, we can write in the product 0.99 to the power 11, and if you calculate this, it is going to be 0.37657 up to 5 decimal places. So probability that exactly one item is defective is 0.37657. Now if we are not interested in calculations, we can use binomial probability table also. So we have this binomial probability tables. Here we are given this type of cumulative binomial probabilities. This table gives us the probabilities of this type, probability that x is less than or equal to small x. So here we require value of small x, value of probability of success. Here it is denoted by capital P, but it is small p in our case. We require number of trials and corresponding value of x in this type of cumulative probability. Now in this case, if you want to use binomial probability table, we can use binomial table also. Okay, so if we don't want to do calculations, or if calculations are lengthy, we can go for binomial table also. So we are asked to find out probability that x is equal to 1. Now we have table for cumulative probabilities. We require probabilities of this type. So here I have to convert this probability into cumulative probability. So this I can rewrite as probability that x is less than or equal to 1 minus probability that x is less than or equal to 0. Okay, we can understand this probability that x is less than or equal to 1 minus probability that x is less than or equal to 0. This means we have to add probabilities up to 1, and this means probabilities up to 0. So there is only one probability, so these two will cancel out, and we have this is equal to probability that x equal to 1. So if our variable is discrete random variable, and if random variable takes only discrete values, then we can always write this type of probability in this way: probability that x is less than or equal to a minus probability that x is less than or equal to a minus 1 if a is integer. So here a equal to 1, so we have probability that x is less than or equal to 1 minus 1, that is 0, or we can understand in this way. So once we have cumulative type probabilities, we can use binomial probability table. So we try to find out this value first. So for this we have to see binomial table. For here number of trials are 12, probability of success is 0.1, and for first probability we have value of x is 1. So we check under n equal to 12, and we consider x equal to 1 and p equal to 0.1. So we use binomial table for n equal to 12. We have probability of success as 0.1, so we will concentrate in the first column, and first we find out n equal to 12. So we can see here we have n equal to 12. This is n equal to 12, and this small x is nothing but 1, and probability of success is 0.1. So we now under n equal to 12 we have to look for x equal to 1 and p equal to 0.1. So these are the values of x, these are the values of p. So for p equal to 0.1 we have first column, so we consider x equal to 1 and p equal to 0.1, and we take intersection. So this column corresponds to p equal to 0.1, this row corresponds to x equal to 1. So at the intersection we have this value. Okay, so we can remove this, and we have 0.6590. Okay, you can check here, first column corresponds to p equal to 0.1. So under p equal to 0.1, and in this row x equal to 1, n is 12. So value of probability that x is less than or equal to 1 is 0.6590. So that we write here 0.6590. Now we check for n equal to 12, p equal to 0.1. Now x is 0 here, so now we check for x equal to 0. So here we have to concentrate corresponding to x equal to 0. So this is n equal to 12, this row corresponds to x equal to 0, this column corresponds to p equal to 0.1. So x equal to 0 and p equal to 0.1, so we have 0.2824. So for that we write 0.2824. Okay, so using binomial table, with n equal to 12, p equal to 0.1 and x equal to 0 and 1, we obtain this. And if you take subtraction, you have 0.3766. So we can compare both the answers. This is up to 4 decimal places, 0.3766, and this is up to 5 decimal places, but if we round off up to 4 decimal places, here we have 5, but this is greater than 5, so we have 0.3766. so answers are same up to 4 decimal places. So that is your choice. Either you can use this formula directly, or you can use binomial probability tables. So binomial tables are helpful if we have large values in the calculations. So that is fine, that is our choice, which method we want to use, either using calculations or binomial probability tables. Now we consider second probability. In the second part, we are asked to find out probability that at least 2 items will be defective. So now we are going for second part. Probability of at least 2 defective items. At least 2 means either 2 or greater than 2. So this we can represent as probability that x can take 2 or more values. So probability that x is greater than or equal to 2. That means we have to calculate all these probabilities, x equal to 2 plus x equal to 3 up to x equal to 12. Okay, so here we have large calculations. We have to calculate probability starting from x equal to 2 up to x equal to 12. So we will not go in this way. We can use the concept of complementary events. We know that if we consider these two events, probability, if we consider this event, x is greater than or equal to 2 and x is strictly less than 2, then these two are mutually exclusive or disjoint events. So probability, sum of probabilities of both the events is 1. So this we can write as 1 minus probability that x is strictly less than 2. Okay, so using this fact, we have this probability equal to 1 minus probability that x is less than 2. Now here x is a discrete random variable, so x is less than 2 is equivalent to probability that x is less than or equal to 1, and we have this probability that x is less than or equal to 1 that we have calculated, which is 0.6590. So we can directly put that probability here, 0.6590, and this is going to be 0.3410. Okay, so this probability we have calculated using binomial table with n equal to 12, x equal to 1 and p equal to 0.1. So this we have obtained. Now if you don't want to use binomial table, then you have to go in this way, using that formula, probability that x is greater than or equal to 2 equal to 1 minus probability that x is less than or equal to 1. So this means you have to go up to x equal to 1. So probability that x equal to 0 plus probability that x equal to 1. Then you have to calculate these two probabilities. Probability that x equal to 0, that means you have to find out value of this probability mass function at x equal to 0. So we have 12C0, 0.1 raised to 0, 0.9 raised to 12. So 12C0, 0.1 raised to 0 and 0.9 raised to 12 plus probability that x equal to 1. So this we have calculated in part 1. In part 1 we have calculated this 12C1, 0.1 raised to 1, 0.99 raised to 11. So that is 0.37657. So that we can write directly here, or we can write one more step, 12C1 0.1 raised to x, that is 1, and 0.99 raised to 12 minus 1, that is 11. So this is now, this is 1, this is 1.9 raised to 12 plus, we have calculated this so that we can write directly. This is nothing but 0.37657. 0.37657. So this is now 1 minus 0.9 raised to 12 minus 0.37657, and I can use my scientific calculator to find out 0.9 raised to 12. So using scientific calculator I obtain this 0.28242, 0.28243. If I round off up to 5 decimal places, I have 0.28243 up to 5 decimal places minus 0.37657, and if I subtract these two quantities, 1 minus 0.28243 minus 0.37657, I obtain 0.34100. Okay, so that is also same as this. Okay, up to 4 decimal places it is same. Okay, so either you can use binomial table or you can use scientific calculator. So this I have done using scientific calculator, or we require simple calculator here. But we can see if we are having binomial probability table, it will save our time. Okay, using binomial table I can directly write this, and within a small number of steps I am able to do this. Now we move towards third part. In the third part, what is asked? Probability that none of the items is defective. So that means all the items are non-defective. So number of defective items is 0. So we have to find out this probability that none of the items is defective. None of the item is defective. This is equal to probability that x equal to 0, and if I use the formula for probability mass function, I have 12cx 0.1 raised to 0, 0.99 raised to 12. So I have calculated this. Here we just calculated probability that x equal to 0, that is 0.9 raised to 12, and its value is 0.28243. So that I can directly write here 0.28243. And if I want to use binomial probability table, I can write probability that x equal to 0. So this I can rewrite as probability that x is less than or equal to 0. And using binomial probability table, we have 0.2824. Okay, we have already seen this. For n equal to 12, x equal to 0, and p equal to 0.1, we have 0.2824. So using binomial table, we have written this binomial table for n equal to 12, x equal to 0, and p equal to 0.1. So here we can write using binomial probability table or using binomial table. Okay, so this is very easy problem. You just have to decide that whether your problem is of binomial probability table or binomial probability distribution or not. So for that you must remember all the 4 requirements of an experiment to be binomial experiment. So we just recall 4 requirements are: number of trials are finite, trials must be independent, for each trial there are only two possible outcomes, either success or failure. So only two possible outcomes for each trial. There must be only two possible outcomes for each trial, and probability of success is constant for each trial. Success is that is our we will decide that out of these two possible outcomes which outcome we consider as success and which outcome we consider as failure. So probability of success is constant for each trial. So if these four conditions are satisfied, given problem is of binomial distribution, and if we have binomial distribution, probability mass function has standard formula NCX p raised to x 1 minus p raised to n minus x. So this is nothing but x is from 0, 1 to up to n. So this gives us the probability of x successes out of n trials. So in this way you must remember these four conditions. If these four conditions are satisfied, given problem is of binomial probability distribution, and if it is binomial probability distribution, we can calculate probability of x successes using this standard probability mass function. So this is all about this session. I hope you like it. Thank you very much.